Start.
Okay. Good morning, everyone. In the previous class, we have seen the integral control. Compared to the simple state feedback control, which will have the controller errors, here we have an additional integrator block which integrates the controller error over time and thus ensures the asymptotic regulation under all parameter perturbations without disturbing the stability of the closed loop systems. So considering the example of a pendulum, let beta be the present state, that is the position of the pendulum, and we need to regulate it at a desired angle delta so that pendulum reaches its equilibrium position, say theta ss, and TSS be the steady state torque which assigns the equilibrium value theta ss at the angle delta. For this we are designing a controller having a control law T is equal to TSS minus K1 into theta minus delta minus K2 into theta dot. These calculations could be sensitive to parameter perturbations and hence the controller errors will be there. So we are going for an integral control approach by considering a system having the state equation x dot is equal to f of x comma u comma w, where w is the term representing the disturbances, and the controlled output equation as y is equal to h of x comma w, and the measured output ym is equal to hm of x comma w. We are designing a feedback controller such that y of t tends to r, a reference value, as t tends to infinity. Assuming that y can be measured and xss at which error is equal to 0 and y becomes equal to r be the equilibrium point at which regulation is achieved. USS be the steady state control required to maintain the equilibrium at the point xss. So we said that integrator integrates the controller error. Integral of error, that is integral E is equal to sigma or sigma dot is equal to E. The state equation of the new system, the augmented system becomes x dot is equal to f of x comma u comma w, or sigma dot is equal to h of x comma w minus r. When we are designing a stabilizing feedback controller that stabilize the augmented state model at equilibrium point xss comma sigma ss. At equilibrium point we can say that sigma dot is equal to 0. Then h of x comma w becomes equal to r, or the controlled output becomes equal to r, which is the desired regulation. So the state feedback control U is designed such that there is a unique sigma ss satisfying the equation gamma of xss comma sigma ss comma 0 is equal to uss, where 0 is the error here. So the parameter perturbations will change the equilibrium point, but the condition error is equal to 0 will be maintained even at the new equilibrium point as long as the perturbed equilibrium point remains asymptotically stable. This was what we seen in the integral control. Hello?
ഒരു മിനിറ്റ്. ഓക്കെ, പറഞ്ഞോളൂ.
Next, we are going to see the integral control via linearization. That is how linearization can be used to design the feedback controller using this integral control approach. Here we are designing a state feedback integral controller. After we augment the integrator to our state feedback system, that is the resultant augmented system equations was x dot is equal to f of x comma u comma w, and sigma dot is equal to h of x comma w minus r. Previously we defined the state feedback integral controller U is equal to gamma of x comma sigma comma e to stabilize the system, and we get its equilibrium points as xss comma sigma ss. But here, since we are going to use linearization, let's define a linear feedback controller for the system as u is equal to minus k1 into x minus k2 into sigma minus k3 into e. Here this equation is actually a linear feedback control law. Remaining portion, that is what is happening when we applying this control law to the augmented system equations, will be discussed by Kavya. Thank you.
ഹലോ
യെസ് പറഞ്ഞോളൂ.
മിസ് എനിക്ക് സ്ക്രീൻ കാണുന്നില്ല, അപ്പം ഞാൻ ഇവിടെ നോക്കിയിട്ട് വായിക്കാം മിസ്. സ്ലൈഡ് മാറ്റി.
ഓക്കെ.
And when the controller equation, that is u equal to minus k1x minus k2 sigma minus k3e is applied to the augmented state equation, we get the closed loop system as x dot equal to f of x comma minus k1x minus k2 sigma minus k3 h of x comma w minus r comma w, and sigma dot equal to h of x comma w minus r, and at the equilibrium point hss sigma hss, the state equation satisfied as, and that become equal to 0, that is 0 equal to f of hss comma uss comma w, and h of hss comma w minus r equal to 0, and here uss equal to minus k1 hss minus k2 sigma ss. Now we want to stabilize this closed loop equation at equilibrium point, and now let us discuss about the linearization of this closed loop. Miss, അടുത്ത slide.
ഓക്കെ, ഞാൻ മാറ്റുന്നുണ്ട്, പറഞ്ഞോളൂ.
At the equilibrium point, and here we choose x delta equal to x minus hss, and sigma delta equal to sigma minus sigma ss, and u delta equal to u minus uss, and thus we get x dot delta equal to a x delta plus b u delta, and sigma dot delta equal to c x delta, and here we know a is equal to dou f by dou x u w at equilibrium point, and b equal to dou f by dou u x u w at equilibrium point, and c equal to dou h by dou x at x w, and Jocelyn will explain about the next part.
Now we can write z dot as x delta dot in matrix form, and we get a x delta plus b into minus k1 x delta minus k2 sigma delta, and c x delta there. Also it can be written as a 0 c0 into z plus b 0 into minus k1 minus k2 into z. Finally we get z dot equal to a cap minus b cap k into z, where a cap equal to a 0 c 0 and b cap equal to b 0. K can be written as k1 k2. So here we are linearizing this integral control independent of w. That means okay, we are designing the k value independent of w such that a minus b k that will be Herbert's. Also here a and b is controllable, also stabilizable, and for such design matrix K2 will be non-singular. Also the xss comma sigma ss, that is the equilibrium point, that will be exponentially stable equilibrium point of the closed loop system. And here the solutions starting in its region of traction approach it as t tends to infinity. Also consequently y of t minus r r tends to 0 as t tends to infinity also. Here the stabilization of excess sigma fs is independent of k3. So we can take k3 as 0. That's all.
Okay.